Assalamualaikum warahmatullahi wabarakatuh. So these are our group for case study of failure of shark column due to 2015 Sabah earthquake. So these are the table of content. For the introduction, as we know, Malaysia has a low seismicity rate, but there are still some places are prone to earthquake. For example, in our case study, near to Mount Kinabalu in Sabah on June 5, 2020, a seismic event with a magnitude of 6 happened. So many of the buildings were damaged due to they are built on the sloping terrain. So the characteristic of earthquake behavior can be predicted with enough precision to be effective in risk mitigation. By integrating geographic investigation of risk survey with estimate and geodetic monitoring of present activity, the potential of new surface fault to trigger future earthquake can be estimated. So we as a team was formed to assess the damage caused by the earthquake impact. So these are the team members that are responsible to do the investigation. The first one is Muhammad Zafri Muhammad Saiful, the earthquake engineer. Amir Iqbal bin Aziz, the construction engineer. Me as a structural forensic engineer. Next is Muhammad Adam bin Jamal as an engineering geologist. Burhan Koyanan as a structural engineer. And the last one is Muhammad Adam bin Nur Azman as an earthquake research engineer. So these team members are be able to recognize and solve problems that arises as a result of earthquake.
For the material investigation, there are several important tests that needed to be carried out during the investigation processes. Okay, for the first test which is the compression test on concrete. So, as an introduction, a compression test on concrete is very compulsory to determine the compressive strength of a hardened concrete. So, basically, it is needed to show the best possible strength that the concrete can reach or achieve in perfect condition. So, the compression test also can show the maximum concrete strength in a hardened state to show the maximum concrete strength in a hardened state. So last but not least, should always be done carefully so that we can avoid bad test results which can be costly. So for the second test, which is the slump test, before leaving the batching plant and on arrival on site. So basically this test is also important to determine the workability or the consistency of concrete mix prepared. So basically the procedure is performed from batch to batch to ensure that the quality of the concrete is consistent throughout the construction process. We don't want any batch of concrete that is not inconsistent, uh, whereby it may result in producing a bad batch of concrete. Last but not least, it can also be used to detect a batch that has been poorly mixed. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adam and I will continue the presentation regarding material investigation. The third method is water absorption test. This method measures the amount of water that penetrates into concrete samples when submerged. It also provides an estimation of the total reachable pore volume of the concrete. This method is tested according to BS 1881122. The last method that we have is ultrasonic pulse velocity UPV. It is a non-destructive test. The velocity of an ultrasonic pulse flowing through a concrete construction is measured to determine the strength of concrete. It is also effective to ensure the quality control of concrete materials and detecting damage in structural components. Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And my name is Muhammad Zafri bin Muhammad Saiful, and I, as the earthquake engineer, will present to you about our earthquake loads. Okay, based on this slide, you can see that we use the lateral force formula, which is SH times with the W is the seismic load. And then for the H, we have the formula that we take from the IS 1893 part 1 that have been reconstructed on 2016. And we can see as the formula we have for a term which is Z. Z is the seismic zone factor, and SA over G is the design acceleration coefficient. R is the response reduction factor, and the I is importance factor. And we assume the soil is stiff soil. And to use the formula, we need to find the Z, which is Z we take directly 0.36 based on the regulation. And for the SA over G, we calculate it based on these two formula, which is TAX and the TAZ. We find the answer is 0.18, which is between 0 to 55. Then we take the 2.5 as the SA over G. And then we use the R factor because we assume that this is a RC building, ordinary moment resisting building, so we take 3. And the importance factor is, since our building is the residential or commercial building, we take is 1.2. And then when we calculate it, we get the AH is equal to 0.18. Alright, for the load, we will take the dead load first. We take as 5 kilonewton per meter, and our floor area is 19.84 meters squared. And then we calculate the UDL, which is the load times the area, and the load is 4, and the load is, we get that. And then we have 3 load actually. We have dead load, imposed load, and the roof load. And the imposed load, we take LL equal to 50%, and we times the imposed load that we take, it is 5 kilonewton per meter. And then we time the area of the floor area, then we get the imposed load, weight of for the imposed load. And for the roof load, which is we take as 10 kilonewton per meter, and the DL, the dead load, we take as 100%, and then we times with the floor area, and we get 918.4. And then for the W, weight of the building, seismic, which we plus them all, and we get the 1607.2 kilonewton. And for the lateral force, we just time with the AH that we calculated earlier, and then we get 289, which is we can take as 300 kilonewton. And that's all for the earthquake, for the load. And I will pass to Rohan Priyanan for the structural analysis.
Hello, my name is Rohan, and I'll be the structural engineer for this project. So we'll be going through the structural analysis. So as you can see, we estimated the point load due to the earthquake. And if we go along, this will be the frame that we'll be analyzing. The point load will be at this location, and we'll be adding a pin support here. So there will be 2 sets of calculations that we will be doing. Both of them MDM. One is due to the forces on the frame, and another one will be the sway. So this will be the assumption for the wall, 15 kilonewton per meter square. We will be doing the MDM method. Again, this is the calculation, this so on and so forth. We will calculate the fixed end moment, and this will be the final moment for the not sway. And then this will be the calculation. So as you can see, there was a pin load to the right. This is the net reaction at the pin load to the right. And this will be for the sway condition. This is the total moment, and again, the same calculation. And this will be the force due to the sway on the pin to the right. As we go along, this will be the final moment. This is the ratio that we got, 0.125. This will be the final moment on the frame. And we will be calculating the reaction at each point. As you can see, the columns are straight. So the forces over here will be the same with the forces down there at the fixed end support. This will be the SFD and BMD. Now, to answer the question why the short column failed, well, the reason is because the shear over here is vastly big compared to the shear over here, and over here. So of course, the shear, the column that is shortest will fail. Obviously, since the shortest column is the one that failed, the shear design for this column and this column is fine. As you can see, there were a lot of assumptions made, but it doesn't really matter. As you can see, the magnitude for the shortest frame is the biggest, the shortest column, and that can be answered due to the SFD that we got. There are a lot of things that we can change, by like increasing the number of columns, or probably just designing it so that it can withstand more shear. So that will be the structural part. Thank you.
I'm going to explain the last part of this project, which is discussion and conclusion. Based on investigation, as short columns were more damaged, common cause seemed to be shear stress. The earthquake force developed at different floor levels in a building need to be brought down along the height to the ground by the shortest path. Due to column height difference in the story level, that is predominantly because of locating building of sloped ground. Short column phenomenon happen. Short column phenomenon is one of the effective causes of building failure in earthquake. Unequal height column cause ill effects like twisting and damage in shorter column as short column is stiffer as compared to tall column and is attract a larger earthquake force. Stiffness of a column means resistance to deformation. The larger is the stiffness, larger is the force required to deform it. If a short column is not adequately designed for such a large force, it can suffer significant damage during an earthquake. In conclusion, different retrofit solutions can be employed to avoid damage in future earthquakes in existing buildings with short columns. Where walls of partial height are present, the simplest solution is to close the opening by building a wall of full height. If that is not possible, short columns need to be strengthened using one of the well-established retrofit techniques. Another solution is that the short column must have a special confining reinforcement called the ductile reinforcement. The reinforcement provided must extend to the column below and above by a certain amount as stated in standards. This solution will eliminate short column effect.